Today I'll talk about a friendly introduction to deep reinforcement learning and policy gradients. So I want to thank Manning for inviting me to their Twitch channel to talk about this. So first I'll tell you that I'm one of the Manning authors. So I wrote a book called Grokking Machine Learning, which is about to go out in press. And you can get the MEP already online. And Manning has provided a code of 40% discount on not only this book but all the books in at Manning, and the code is Twitzer40. So I'll be displaying it again later, but feel free to use it. So in this book, I talk about supervised learning, which is one of the branches of machine learning, probably the most popular and the first one that one would learn. But in this talk, I will tell you about something different. I tell you about the, reinforcement learning, and it's something I touch in the book briefly, and it uses a lot of things that are in the book, but it's not there. It's a more advanced topic. So I will first tell you about some applications of reinforcement learning. So some applications are pretty much all the cool cutting edge stuff. So self-driving cars use reinforcement learning. Robotics use reinforcement learning, and things like playing Go and chess. You know how the computers already beat humans at Go and at chess. These are applications of reinforcement learning. Because pretty much reinforcement learning is about doing tasks. So, for example, in predictive machine learning, which is what we learn on the Grokking Machine Learning book, then you have a bunch of data. And with that data, you build a model and use that model to make predictions, to answer questions like yes or no, or to give you numbers, etc. Reinforcement learning, on the other hand, you don't have the data. You simply have an environment, which can be a grid or something, or a game, or a terrain, or a city with streets, or just anything, a bunch of points. And you have an agent, and the agent is the one that acts. And so the agent basically moves around the space looking for prizes or punishments or anything like that. And in that way, it collects data. So it's a completely different problem, although similar techniques that work for one work for the other one. And so in this talk, I will tell you about several things. One is Markov decision process, then the Bellman equation, Q networks, and policy gradients. So we'll get to each one of these at the right time. First, I'll tell you about Markov decision processes, which is the simplest version of reinforcement learning. So here's the main setting we have today. We have something called a grid world, which is just a grid with squares. And we have an agent, which is this little dot over here. And the point is that the dot moves around the space, and there are some boxes that have special things. For example, if you land here, you get a lot of money. If you also land here, you also get money. And here there is a dragon, and that dragon eats you if you fall there, and you lose the game. So you win if you get to the money, and you lose if you get to the dragon. And so just to put some points, you get 5 points if you get to the money on the top right, 4 points if you get to this money, and -1 if you get to the dragon. That's the rules of the game. Furthermore, there are some barriers, and you cannot cross those barriers. So the point is to teach the agent to play this game and win as many points as possible. So for example, if the agent does this, then it gets a 4, and you record that. But if the agent does this, then it loses 1 point, so we record that. And if it does this, then you get a 5. You don't have to start in the bottom left corner. You can start anywhere you want. So that's the game. Now we're going to figure out a strategy for the agent to win at this game. Okay, and so for that, I'm going to teach you a bunch of things: value, states, actions, and policy. So value and policy work in the following way. Imagine that I'm going to have one of the squares in the grid. That's the one on the right. And let's say that it has 4 neighbors. It doesn't have to have 4 neighbors. Some don't have 3 or 2. But this one, let's say it has 4 neighbors. And so each of the boxes is called a state. And the actions are the 4 things you can do. So you can go up, down, left, and right. And there are some values. So I'll tell you a bit more about this in a minute. But imagine that going to the right, you win 4 points. Imagine that going up, you gain 1 point. Going to the left, you may lose 3 points. And going to the bottom, you gain 2 points. So that's what we have so far in this particular square. So then if the question is, where would you want to go, right? If you're in this situation, where would you want to go if you want to gain the most amount of points? Well, clearly you would want to move to the right? So these are the values, by the way. Everything in a box is a value. So the -1, the +5, and the +4 you see on the left are values. And so clearly we want to move to the right. So the new value for this box is 4, because it's the maximum I can get if I play intelligently, right? I get a 4. So in that way, the equation basically says that the value of a box is the maximum of the values of the neighbors, because if I have a neighbor with high value, I can just walk towards there and win. So what happens now? Well, look at the neighbors of 5, right? The neighbors of 5 are gonna get values of 5 because they can easily walk into the 5. And the neighbors of 5 will also have a value of 5. And actually pretty much anything will have a value of 5, because from anywhere I can walk towards the 5 and gain 5 points. So this is a pretty easy game. And don't worry, we'll make it harder. But this is a pretty easy game. Basically we have something called a policy, which is the arrow that points at where you should always move. I think of it as a supermarket during COVID with arrows on the floor. That's it. Go in this direction, go in this direction. So if the policy here is pretty simple. It's basically try to walk into the 5 and try to avoid the 4 and try to avoid the -1, because if you walk into the 4 or the -1, you don't gain 5 points. And so the idea is, this is a good policy. It says, follow any of the arrows, do whatever you want. And if you walk into a wall, you stay where you are. So you just don't lose anything. So that's a good policy. Obviously that policy may make you walk around a lot and may make you waste time. So maybe something like this is better, where you don't walk into walls. And there's still something much better, right? Like we can still do a little better. So for that, now I'm going to teach you something that will help you not make the robot walk in circles forever and just waste time. And for that, we go to the rewards. So the rewards is basically, we don't want the agent to be moving around. We want the agent to go straight to the money, right? And for that, we're going to create it can be a reward or a punishment, but it's called a reward. So we're in the same scenario as before. You can go, if you go to the right, you get 4. If you go up, you get 1. If you go to the left, you get -3. And if you go to the bottom, you get 2. So obviously here we want to move to the right. However, now we're not going to say that we gain 4, because it's expensive to move a robot 1 box. So we're going to lose 1 point every time we move the robot. So it's like gasoline or something. It just wastes energy. And so this is the reward of -1. So if I move into a 4, I now have a 3. If I move into a 1, I now have a 0. If I move to -3, I now have a -3. And if I move into a 2, I now have a 1. And now I still pick among the maximum of this. So I still want to move to the right, except that now I have a 3. So my new equation, it says that the value of a box is the maximum of all the neighbors of -1 plus the value of the neighbor, right? It says basically always move until always move in the direction of your highest neighbor, but every time you move, you're going to lose 1. And that's going to prevent the agent from walking aimlessly, because it's going to lose points when it walks aimlessly. It's just going to want to really get to that 5 or that 4. So here's the neighbors of 5 now have value 4, because you walk into the 5 and you get you subtract 1. These ones have value 3. Now let's look at the neighbors of 4. they have value 3 because you can walk into the 4, right? Now these have value 2, and we can continue propagating this, right? And the neighbors of the 1 minus 1 will have a value of minus 2. And sometimes we'll propagate this and we may have to recalculate some things. That's completely okay. But let's propagate it like this. So take a look at this, and I hope you agree with me that the values of each box is that, because you can always sort of walk, if you walk into the direction of the increasing value, you will get to the most points you can get from that particular position. So here's a policy. It's a policy that always points into the square of highest value. So what happens here? Let's say that our agent is in the bottom, the orange agent, right beside that minus 1. So the policy says walk into the minus 1. Why would one walk into the minus 1 and lose a point? Well, because it's better to lose 1 point by walking into minus 1 than going all the way to the 5 and losing many points, right? If you think about it, I like to imagine, if you go all the way up, you lose a lot of points. You gain 5, but you lose a lot more points. Whereas if you walk towards here, you only lose 1 point. I think of it as if, like, if you are somewhere outside of your house and you really have to go to the bathroom, and there's a really nice one like 10 kilometers away, but you don't want to go that far. You're in a rush, so instead you kind of go to the okay one, or maybe the not so nice one, because it's much closer. So it's just a strategy that you play, right? So this game makes us change our strategy. There's another way that makes us change a strategy with the discount factor. By the way, if there's any questions, feel free to ask them in the chat. I can see the chat right here. So the discount factor is similar to the reward. What it does is it says $1 today is worth more than $1 tomorrow, because it's better to have my money today than if I'm gonna receive it tomorrow, right? I can put it on interest, or I can do whatever. And the same thing with the day after. Every time I earn $1 later is worth a little less than if I have it today. Let's say that today is worth 1 and tomorrow is worth 90 cents because my discount factor is 0.9, and the next day is worth 0.9 times 0.9, which is 0.81, and the next day and the next day. Every time a day passes before I get my money, it's going to be worth every dollar is going to be worth 90 cents of what it was worth the previous day. And so again, that 0.9 is the discount factor. And what we do is that every time we make a step, if we walk into and get a 4, then the previous box is not going to have a 4, because the 4 is what we get tomorrow. Today I'm going to have a 4 times 0.9. So if I walk into this 4, I get 4 times 0.9. If I walk into the 1, I get 1 times 0.9. And the same thing for all the other boxes, right? It's always what you get times 0.9. And you still want to go into the best one. So you still want to go into the 4. And so my new equation now says that the value is the maximum of the values of the neighbors times the discount factor, which is 0.9. So now it's going to be 3.6 because I still want to go towards the 4. It's my best strategy. But I multiply by value by 0.9. So if I'm going to start filling my squares, well, the neighbors of the 5 get 4.5, which is 5 times 0.9. Their neighbors of the plus 4 get 3.6. And you can continue propagating this and notice that these are the values. So if I'm at any square, I can walk towards either the 5 or the 4 and gain that many points. So here's a policy that points into the direction of highest gain every time. So, all right. So now we can combine everything into something called the Bellman equation. And what the Bellman equation does is combine the two previous ones. So we had an equation with a reward that would lose 1 point every time we make a step. And we have another one with the discount factor, which multiplies it by 0.9 every time we make a step. And so the total value equation, we can combine these two. So every time you make a step, you lose 1 point and your money multiplies by 0.9 that you would have earned there. And that's the Bellman equation. These are the values of the states. these over here are the actual states. The actions are A in blue. Those are going up, left, down, and right. The reward is in red, is the -1. And the discount factor is the 0.9 that you lose every time that your money multiplies every time. So the actions again, up, down, left, right. The reward is -1 and the discount factor is 0.9. So if I have a box, for example, this one with my 4 neighbors, I always want to walk into the one of maximum value, but my new value here is calculated as 4, which is what I win, times 0.9 times, -1, so it's times the discount factor minus the reward, so 2.6. So that's how I'm going to propagate my values. Now, for this talk, I'm not going to use a discount factor because that makes the numbers messy. So I'm really just going to say actions is up, down, left, right, reward is -1, and the discount factor is 1. So let's forget about that thing where you lose, where your dollar tomorrow is worth 90 cents of a dollar today. The dollar tomorrow is worth exactly like a dollar today. We're just only going to lose 1 point for moving. So now let me show you how to solve this Bellman equation, because I've told you about the Bellman equation, but how do we solve it? Well, the way we solve it is very simple. We start picking random boxes. We pick this box, and well, we don't know anything about this box because the neighbors don't have any value, so we skip it. Then we pick this random box, and again, the neighbors don't tell us anything. And so we don't know very much, but then one day we get here. And if we get here, then one of the neighbors is +5. So because one of the neighbors is +5, my value here is 4. Because remember, I lose one point every time I move to a box. So I can guarantee that if I'm here, I can guarantee a 4 by moving to the right. If I'm here, I can guarantee a 3 by moving down. If I'm here, I can guarantee a -2 by moving to the right, to the left, and earning -1 points, right? And I can continue. If I'm here, for example, I can guarantee a 2 because I walk to the left and get a 3. If I'm here, I can guarantee a 1. And if I'm here, I can guarantee a 0. Again, applying the Bellman equation. But now look at what happens. If I'm here, Bellman equation says the maximum of the neighbors -1. So it's a 3. But now that 0 underneath has to change, because now the value for that one is not a 0, but it's a 2, because the one on top is a 3, right? So remember, the maximum of the neighbors -1. And so you may have to recalculate these values, and that's okay. You just go over all the boxes, recalculate, recalculate, until eventually, I hope you believe me that if you do this many times, you'll get a full grid with boxes completely numbered with the actual value. So that's how you solve it. And then to get the policy, you simply, at every point, you draw an arrow towards the highest value around you. So the highest of your neighbors that says always walk. So notice that if you're close to the 5, you kind of walk into the 5. If you're close to the 3, you kind of walk into the 3. And actually, there's a small mistake there. You want to walk into the 1 when you're in the bottom right. But anyway, here's the problem. That required a lot of computation because you have to walk into every single box many times. That's not good. Because imagine if you had a humongous grid with many boxes and many actions. Well, by the time you fill this in, it's going to take forever. So what we do is we fix this using neural networks. So it doesn't matter if you don't know what neural network is, don't worry. I'll show enough of what we need to know. But a neural network looks like this. And we're going to have 2 networks, one for value and one for policy. If you want to learn more about neural networks, I'll give you 2 options. One is to take a look at this video that I have on YouTube. You can search for a friendly introduction to deep learning and neural networks. Later, I'll show you my YouTube channel. Or you can read Grokking Machine Learning, where I have an entire chapter on neural networks. So we have all the explanation of how they get trained, how they solve problems with an example of image recognition, and how to code them. So take a look at that. And but going back to this, the idea is that we don't want to visit every single box. We want to visit a bunch of them. And with that information, we want to sort of propagate it to the entire network. That's what we're gonna do. Because here in this grid, we have way too much information. What we would love to do is to store it in less. For example, if we were gonna solve the problem of winning in a game of Go, then every configuration of the board is a state, and any action that you do, any pebble that you put, is an action. And so there's already more states in a game of Go than the number of atoms in the known universe. So you wouldn't be able to store all that information, all those values. You will not be able to store them, even if you manage to store something in every atom of the known universe. So you need to crunch this information into a much smaller space, and that's what we use the neural network for. But before we get into neural networks, let me tell you a bit about the strategy that we're going to play. The strategy is very well known in reinforcement learning, called explore exploit. So there are two types of strategies. One is called deterministic and one is called stochastic. And let me tell you a bit about sort of how it is. It's just a way to search the space for solutions. So let's say that we have our agent here, and there's some money there, and there's a lot more money on over there. And let's say that we have figured out a policy that says walk towards the dollar bill, and so it says, only walk towards the dollar bill. So deterministic policy. Now, if you don't give the agent the chance to explore the space, that the agent may never figure out that there's a lot more money upstairs. Once the agent figure out some small price, it will continue going towards that price, and it will never be able to explore the rest. However, if we have a much smarter policy, it's a stochastic policy, where you say, you know what, agent, I think I just found out there's a bill in front of you. So walk towards that one with much higher probability, but still give the other chances, the other directions a chance. So you can still go up with some small probability, and left to some small probability, and right to some small probability. And at every point you have some combination of arrows, and then you make the agent walk, and the agent will walk a little aimlessly, which may not get to the bill as fast as the other agent, but it has chance to explore the space and maybe find out a lot more money upstairs. So that's the difference. And the second one is called a stochastic policy, and it's much better than a deterministic policy. So we're going to use a stochastic policy. A deterministic policy is the one that always tells you one arrow, and it says basically always move to the right, or always move up, or always move left, from that box. Stochastic policy will say, okay, you want to move towards the bigger number, so we're going to give you a higher, you're basically going to flip a coin, or roll a die with 4 faces, and with 65% probability, let's say you're going to move right, which is the highest value, and with smaller probabilities, you're going to move up, left, and down. And that's what we're gonna do. We're gonna do a stochastic policy. So in the left, we have a deterministic policy that basically tells the agent where to walk with no room for exploring, whereas the stochastic policy will tell the agent how to move around the space, but it'll give it room for sort of moving around and exploring a little more. So given that, I'm going to tell you about neural networks. So why do we use neural networks? Again, for the reason I told you before, is because we don't need to visit every single box, right? A neural network, we don't have time to visit all the boxes several times. So what we're going to do is we're going to use the following observation. Let's say that I have figured out the value for this box. Well, whatever the value for that box is, it's got to be similar to the ones around it. Because if I make a lot of money by being in this box and walking intelligently, then probably from similar ones I make similar amounts of money. And the same thing for its neighbors and its neighbors. So basically, the value for a box really influences its neighbors. In the same way, if this is a very bad zone, then the neighbors are also a very bad zone, and their neighbors are also in a bad zone, and so on. Because, as I said, the value of a box really influences the neighbors. And so what we're going to do is we're going to take the coordinates of the box, x and y, and put them into a neural network, just as a function with an input and an output. And the output's going to be the value for that box. Okay? So that's how the neural network's going to look. Input are the two coordinates of the box, and the output is going to be the value. And so that's the value neural network. Now the policy neural network is going to be similar, but it's going to come it's going to be based on the premise that if the policy for this box with coordinates x, y is this one, it says go up with higher probability and then to the right with a slightly less and so on. Well, the neighbors probably have a similar policy, right? Because you probably want to walk in the same directions if you're in boxes that are close to each other. So therefore, by only knowing the policy and a few points, I can sort of interpolate the others. And that's the concept of a neural network again. So for the policy neural network, I am going to input two things, which are the coordinates of my point, and I'm going to output four numbers. And those four numbers are the probabilities of going in each one of the four directions. So that goes there. So basically it's a neural network that if I enter two numbers, I output four numbers. So I enter the coordinates of the point and I output four numbers that add to 1, which are the probability of going up, the probability of moving right, the probability of moving down, and the probability of moving left. Okay, so in summary, we have the value neural network, which guesses the value of every point, and the policy neural network, which guesses, sorry about that, the probability of going in each of the four directions. So I will now tell you about each one of them. How do we train a value neural network? So here's the premise, okay? If we have, basically the idea of the network is if we have this value, we kind of know a little bit of the neighbors. And if we have this value, we kind of know a little bit of the neighbors. And we can continue like that until we know all the information there is. So again, the input, for example, if I want to find the value at the 0.45, I just use the neural network to get a value 4, and that's going to be my value. Okay, so I'm going to tell you how to train it. The way we want to train it is by forcing the neural network to satisfy the Bellman equation. Remember that Bellman equation that it says always move in the direction of the maximum, and the maximum value, that your value is going to be the maximum of the values around you plus the reward and times the discount factor. So let me do a small one over here. Let's say that we have a neural network that we have initialized, right? A neural network, again, you can think of it as an input and an output, and you want to find the right neural network that gives you the output for what you want. Okay, so let's look at the box 2, 3. Okay, the box 2, 3, if you put 2, 3 in the neural network, is going to output some value. Let's say it's 0.2. So that's going to go here. Now let's do the same thing for the neighbors. We put in 2, 4 and get another random value. These values are pretty much random because the network hasn't been properly trained. So it gives us a 1.3 for the one on top, a minus 2.7 for the one on the left, and let's say it gives us, for the one underneath, a 4.9. So now we have the same scenarios in the beginning, right? What would the value be for the one in between, in the middle? Well, it would be the maximum over all the 4 actions I can do, over all the 4 neighbors, of -1, the reward, plus the value of that state. So therefore, my neighbors are 3.2, 1.3, minus 2.7, and 4.9. So if I subtract 1 to all of these, I get 2.2, 0.3, minus 3.7, and 3.9. And so I pick the maximum of those, and my value should be 3.9. So it used to be 0.2, now it's got to be 3.9. So I'll tell the neural network, you know what, neural network? For the 0.32, I don't want you to give me a 0.2 anymore. Now I want you to give me a 3.9. So we tell that information to the neural network. Neural networks do that. They take features and labels, and they try to match the features as they input with they try to output the correct label to the feature. So it tells, you know what, when I give you a 3.2, try to output a 3.9 more. And so that's what the neural network does. Now the neural network takes tiny steps, so it's not going to go all the way from 0.2 to 3.9, but it may get you farther. And the way you train it is using an error function. So the error function is going to be, how far are you from satisfying the Bellman equation? So if you have your value is 0.2, and your error, your the value according to the Bellman equation should be the maximum of those four things, which is 3.9. So your error function can be what you have minus what you want squared. So that gives you a large number. And so if you do this many times, you'll train the neural network to the weights to get a little better and to give you a better value. It's not going to go all the way to 3.9, but it may be 0.45 or something. It's just going to slightly increase. And so you can imagine that if you do this many times, if I take a box, apply the Bellman equation and train the neural network, if I take another box, apply the Bellman equation, and so on, I will eventually start training my neural network to become better and better and better at predicting these things. And there's going to be a point where this neural network is just going to be beautifully trained, and it's going to catch all the values of the value function. So that's pretty much how you train a value neural network. And then now when you have an agent, all the agent has to do is walk into the direction of the highest gain at every point. Okay, so we managed to find all the values without visiting every box. So now let me tell you about the policy neural networks. Are actually a little bit more popular than the value neural networks, and they work like this. So recall that what I want is to build a neural network that if I input the coordinates of the point, it outputs four numbers which add to 1, which are the probabilities of going up, left, down, or right. And it looks like this. It has 2 inputs and 4 outputs. These outputs are the 4 numbers that tells us with how much probability to go up, right, down, or left. So let me tell you how to train this neural network. Okay, the way to train it is the following. Let's say that we have some random initialization, so random weights, and it's going to give us some values for each one of the directions at each box. It's probably not the one we want, but let's make an agent walk given those probabilities. So let's say we have that path, and now let's calculate the value of these boxes given that path. So if I walk into a 4, then my value is a 3, because remember that the cost for walking one box is 1. If I walk into that one, my value is a 2, and for this one is 1, for the next one is 0, and for the next one is -1. So basically along my path I keep subtracting 1. Okay, and now what I'm going to do is I'm going to create a small data set, and that small data set I'm going to be sending it to the neural network. So what I'm going to do is, for each point, the gain is the value at that point according to the path, and I'm going to have the coordinates of the point and the direction in which I went. So I do this for every single one of the points. Sorry, it's a little slow. Okay, and now I'm going to do the following. I'm going to tell the neural network to increase some of these directions and decrease them according to the gain. So I'm going to tell the neural network, you know what? When you're in the box with coordinates 0, 2, that was pretty good because it gave me a 3. So please increase that the probability of that direction. When I'm in the box with coordinates 0, 1, that gave me going up gave me a 2. So that's pretty good. So increase that direction, the probability of that direction. When I was in the box with coordinates 1, 1, and I moved left, I made 1 point. So it's good. Increase it. When I'm at the point 1, 0, I moved up. That gave me 0 points. So don't worry about those. And when I'm at the point 0, 0 and I move right, I actually lost a point. So decrease that probability. So I'm going to tell the neural network to do all these things at the same time. I'm going to feed all that information to the neural network. And I'm going to tell you in a bit how to do this with math. But basically it's that. So let me do it one more example. I'm going to walk in my step in my according to the policy that I have. I'm going to number each one of the elements in the path with one less, because each time that I walk I lose a point, and at the last one I make 5. So previous one is 4, then the previous one is 3, 2, 1, all the way to -3. And I'm going to create my data set. First I'm going to look at all the directions that I went. These are the directions, and these are the directions that I'm going to tell the neural network to update. So I'm going to create my data set with the gain, the coordinates, and the action. So for each point, I have the gain, the coordinates of the point, and the action that I took. Now, some of those actions were good, some of them were not so good. Which one was good? The one that gave me 4 points. Which one was not so good? Well, the one that gained me -3 points was pretty bad, right? So for that one, I tell the neural network to think of it less. Whereas for the one that gave me 4 points, I'm going to tell the neural network to improve that one. Okay, so I'm basically, sorry, it's lagging a little bit. I'm telling it to increase the probability of going right when you're at the 0.45. I'm telling it to slightly increase the remaining ones and keep going down until you decrease the final probability, the one of moving left when you're at 3, 1. Sorry, there's a little lag in my slides. So then I feed all this information into the neural network. Okay, so I tell it, you know what? Some of these arrows are good, make them bigger. Some of these arrows are bad, make them smaller. And I give all that information to the neural network. And I continue doing that. So if I do that forever, I continue doing that many times, always feeding that information into the neural network, and eventually I will have something that is pretty well trained. Okay, so I take another path, I take another path, and so on. So eventually I end up with something pretty good. I end up with a pretty decent policy that will tell me how to walk in the best possible direction. Okay, and I'll tell you very briefly about how to train the neural network. Basically, if you think of this is more for people who know who have trained neural network before. If you have, the way you train neural network is by features and labels, right? So you train it so that it gives you the right label according to the features. And so what you do, if you wanted, for example, to output a 1 when you say 4 or 5, then if the neural network's outputting anything else, for example, a 0.2, that's what you got. What you want is the 1. So you tell the neural network to increase that 0.2. And actually, because of derivatives, you want to do gradient ascent, and you actually tell it to increase the logarithm of 0.2. So that's the gradient ascent step. Well, if you're going to train the policy network, then you do something very similar, right? Instead, you want it to, let's say that your input is 4 or 5, and your output is the direction that you took in the path. And so let's say that the probability that the neural network gave you was 0.2, and what you wanted was 1. So you tell the neural network, you know what? I want you to increase what you gave me for those features. So increase the 0.2, and actually because of gradient ascent, I want to increase the logarithm of 0.2. Except that remember that we had a gain, right? So we had the gain that if it was good, I want to increase that probability, and if it was bad, I want to decrease it. So if my gain was, for example, 4, I do a trick, which is that I increase 4 times the logarithm of 0.2. So I have that. That is my new gradients and step. So it's bigger if the value is higher. So I increase more if the gain is higher. And if the gain was, for example, -1, if it's -3, if it's a bad step, then I use that in my gradient and step to actually decrease the probability of going in that direction. So this part is a little technical, but it's just to tell you that it's a small trick that we use to train the policy network. And then finally, when we have the trained policy network, then all we have to do is use it, right? So this is a small summary. The way you train it is by taking random paths. With those paths, you build a small data set, a small data set with the gain and the coordinates of the point and the direction that you want to go, or that you went in that particular path. It's lagging a little bit. So you have the gain, you have the coordinates, you have the action, and the neural network returns some probability. Well, you want to increase the ones on the top and to decrease the ones on the bottom, because you want to increase the ones with high gain, decrease the ones with low gain. So therefore, you increase the logarithm multiplied by the gain, and that way you do a trick. Sorry, my lights are about 10 seconds behind me. Not too much running in the computer. And that's it. That's pretty much what policy gradients are. So once you have the policy gradient, then you simply have your agent. You have your neural network. The neural network tells you which direction to move because it gives you the 4 probabilities. And then you just follow those probabilities. You take the input. The input is the coordinates of the point. The neural network spits out 4 probabilities. So you use those 4 probabilities to tell you with what probability to move in each direction, and then you move in the direction that your policy tells you. And in that way, you gain at the game. You win the game. So that's all I have. So thank you very much for your attention. And if you have any questions, feel free to ask them on the chat. And again, I'd like to remind you that this is the book I wrote with Manning editors, Grokking Machine Learning. And the discount code is TWITSER40. So write it down. And it's not only for this book, but it actually is a discount code for the entire catalog at Manning. So feel free to go use it. And other ways to follow me, if you want to follow my YouTube channel, I have lots of videos like this one. You can find me as Luis Serrano on YouTube. And this is my Twitter handle, Luis Likes Math. And my page where all this information is, including the book and discount codes, is serrano.academy. So thank you very much.